Assalamu alaikum. I am Muhammad Akramul Khandukar, an undergraduate student of Asanullah University of Science and Technology. Today, I am going to present our work on comparative analysis of 8T, 10T, 12T, 14T full adders, accompanied by Tasneem Azad, Mustafa Habib, Habiba Bushra, and Mahbubur Rahman. The adder is the most important part in any controller design. Full adders considered as the major component in arithmetic logic unit. Digital signal processing chips and microprocessors gain much interest among researchers over the years. As a result, various adder cells have been developed by employing various logic styles. It is necessary to have a complete overview of the various sorts of full adders to figure out their performance level. The power consumption for CMOS circuit is given by the following equation, where we clearly say that the power depends on different parameter as well as on the supply voltage. Lowering the supply voltage would significantly lower the power consumption of the circuit. This basic concept would be used to improve the performance of adder circuit. At early stage, VLSI design used complementary pass logic, which uses only NMOS to implement full adder cells. However, due to excessive power loss and transistor count, complementary pass logic was replaced by static complementary technique that employed both PMOS and NMOS transistors. Adder which employs two or more logic styles is called hybrid adder. Nowadays, researchers are focusing on hybrid adders to utilize the advantage of various logic styles for improving performance aspects. In this paper, we have an analytical and comparative description of various full adder circuits. The circuits are designed in Virtuoso platform using Cadence tool with the available GPTK90 kit. In this paper, our motive is to make the design efficient to reduce the power consumption, delay, and the area of the logic circuit, while maintaining low complexity of logic design. Here comes Tasneem Azad to talk about the basics of full adder circuit.
Hi, I am Tasneem. Before going to discuss about different kinds of full adders, we have to know the basics of it. Half adder circuit has a major drawback that we cannot provide carry in bit for addition. In the case of full adder construction, we can provide carry in as an input in the circuitry and could add it with other two inputs. So, in the case of full adder circuit, we have three inputs from where we will get the final output sum and carry out. For full adder circuit construction, we normally add two half adder circuits with an extra addition of OR gate. Here you can see the block diagram where two half adder circuits added together with an OR gate. The first half adder circuit is on the left side. We give two single bit binary inputs. It will provide sum out and carry out bit. This sum is the final output of the full adder circuit. On the other hand, the carry out of the first half adder circuit and the carry out of second half adder circuit is further provided into OR logic gate. After going through the OR gate, we get the final carry out. The final carry represents the most significant bit. We can also express the full adder circuit construction in Boolean expression for the case of sum and carry out. Now let me give the platform to Mustafa Habib to let us have a look at the different full adders that we worked on.
Thank you, Tasim Azad, for giving me the platform. I am Mustafa Habib. Now I am going to introduce different type of full adders that we worked on. Normally, different architectures are used to design full adder circuits. The less transistors we can use, the more efficient it will be. Moreover, less transistors reduces power consumption. The development of 14T full adder led to better results for delay as well as power consumption. However, the adder didn't show improvement in threshold power loss. Hence, the 14T adder would consume significant power as compared to the presented 12T, 10T, 8T full adders. In 8T full adder, it doesn't suffer from threshold power loss problem. Also, the noise margin can be substantially decreased by proper sizing of transistors. In our project, we simulated four types of full adder circuits using Cadence software in 90 nanometer CMOS technology. At first, we designed the schematic diagram, then we generate the layouts of the circuit using Layout Excel. Then we run DRC to ensure all the design rules are maintained. Then we compared layout with the schematic design to make sure if all the parameters and pins are being matched. Here you can see the design of schematic diagram of full adder using 14 transistors, and this is the layout of that adder circuit. Then we used Ashura technology to run DRC and LVS where no error is found in DRC. And in LVS, schematic and layout were exactly matched. We followed the same procedure to design schematic and layout for 12T, 10T, 8T full adders, and then we run DRC and LVS, where we found no error in DRC and the schematic and layout were exactly matched every time, as you can see in the figures. Let me call Habiba Bushra to talk about the merits and demerits and troubles we faced while designing the circuits.
Thank you, Mustafa, for giving me the opportunity. Talking about VLSI circuits, having optimum level of delay and power have become more crucial. Modern portable electrical devices requires fast computation utilizing least amount of power. Therefore, different type of adder cells have been developed over the years, each having its own advantages and disadvantages. 80 is a low power, high performance full adder whereby optimizing the transistor size, power, and delay can be minimized. It has better control in leakage current, static, and dynamic power dissipation, but it lacks driving. However, in 10T full adder, it requires less area compared to higher gate count. Because of poor driving capability, voltage drop occurs, so it cannot be operated in latest technology. In 12T, delay decreases faster with the supply voltage, though power loss limits its uses in portable devices. 14T leads to high input impedance, which causes unsatisfactory performance level, though it has lower surface area in terms of other bigger circuits. While designing those circuits, many prospects were kept in mind. Best one can be chosen based on required applications. For example, if we consider area as the main factor, then the designers can prefer 80 full adder design which has lesser area. And similarly, if we consider power consumption as the main factor, then the designers can prefer 14T full adder design which has lesser power consumption. Now Mahabub will tell us about the future work and give us a conclusion on the project we have been working on.
Thank you, Habiba. Well, Low power is the demand of modern age. The low power VLSI research open new technique for reduces power in the field of processing and adder. As a future work, we can extend the work by applying different architecture of full adder using different gates. We can improve the performance of each of these designed 1-bit full adder blocks by varying their cell ratio or by adding some of the passive elements like resistors or capacitors. Using the designed 1-bit full adder blocks, we can design multiple bits adder circuits. We can even design and compare their designs in all possible nanometer technologies like 180, 90, 65 nanometers and so on. We can replace the full adder blocks of any previous application projects with new designed full adder circuits that can do the same function as that is done by the old one and improve the performance factors like area, delay or power consumptions. Finally, it can be said that a comparative study on various existing full adders have been conducted. Since various sorts of adders employing different techniques and logic styles have been developed by researchers over the years, it is necessary to analyze their performance aspects to figure out strength and weakness. Pros and cons of the adders have been discussed in details. For analyzing performance parameters, the adder cells have been implemented and simulated using Cadence Virtuoso tools. Standard 90 nanometer technology has been used for all simulation cases. We believe that the comparative analysis among full adder cells in this paper will enable VLSI designers to find out the best suited full adder cells depending on system requirements. At the end, we would like to thank Professor Dr. Satyendranath Bishwas for his supervision. We would also like to thank Faisal Noyan, S.M. Ishakul Haq and Shani Rahman for their continuous help. Thank you all.